I now call to order the Society's 2,437th meeting in the 150th year since its founding on March 13, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 meeting and lecture series. Because of COVID-19, the Society is bringing this meeting to you via Zoom from locations all around the globe, rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. This evening's lecture will be about the Clipper mission to Jupiter's icy moon, Europa. Our speaker is Kate Kraft, staff scientist at the Johns Hopkins University Applied Physics Laboratory, and staff scientist on the Europa Clipper mission. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington, to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join 150 other recordings of PSW Science lectures. We invite you to explore these presentations and to become a member through the PSW Science website, www.pswscience.org. Last Saturday was the 150th anniversary of the Society's founding on March 13, 1871. Because of COVID restrictions, we could not gather all the members together to celebrate the occasion. But members of the General Committee commemorated the anniversary day on the National Mall at the statue of Joseph Henry in front of the Smithsonian Castle, where the Society was formally founded. We recited some of the Society's history and toasted the founders, the members, the Society, and its future. We raised our glasses on behalf of all PSW members to celebrate the Society's first 150 years and to wish the Society even better fortune and success in the next 150 years. We are all looking forward to celebrating the Society's first 150 years in person, together, sometime this year, when we are able, once again, to meet in person. We will keep you posted on these plans as they become clear. In the meantime, please join me in toasting the Society's 150th year. To the Society, its members, speakers, and long legacy of promoting science and the exchange of scientific ideas. The Society is grateful for the sponsorships of the 2021 lecture series by the Policy Studies Organization in cooperation with the American Public University, and by a generous donor who asked to remain unnamed. We thank all of our sponsors. Before we turn to the lecture, in keeping with the Society's traditions, we will welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce the following members have been elected to the Society. Roger Mann, a mobile app developer interested in software design, quantum mechanics, astrophysics, and Europa, who learned of PSW some time ago and has been watching videos of previous PSW meetings. Eric Enig, an engineer with Enig Associates, interested in magnetohydrodynamics and electromagnetics. Eric is a returning PSW member who learned a PSW from his father, longtime and mother, longtime PSW members Julius and Mary Enig, who were both presidents of the society. And Kate Kraft, our speaker tonight, who learned of PSW through our invitation to her to speak tonight. Some of her interests will be clear from tonight's lecture. We welcome them all. For those of you who are not members, please note membership is a most important pillar of the society. I encourage everyone with an interest in science to become a member. It's easy to do using the PSW Science website homepage, www.pswscience.org. PSW is a 501c3 charitable education and professional organization. Dues payments and other donations to PSW Science are tax deductible. Recording Secretary James Heelan will now read the minutes of the 2436th meeting and the lecture by Jim Fanson on building the Giant Magellan Telescope.
Thank you, Larry. Good evening, everyone. On March 5th, 2021, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2436th meeting of the Society to order at 8:02 p.m. Eastern Standard Time. He announced the order of business and welcomed new members. The recording secretary then read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, James Fanson, project manager for the Giant Magellan Telescope. His lecture was titled, Building the Giant Magellan Telescope. The human eye has an aperture of approximately 0.2 centimeters squared and requires assistance to see further than the Andromeda Galaxy, approximately 2.5 million light years away. Since Galileo's telescope in 1609, the aperture diameter of telescopes has doubled approximately every 30 years. Galileo used a 2.6 centimeter lens in his telescope. Almost 300 years later, in 1897, the Yerkes telescope reached the practical limits of refracting telescopes with its 1 meter lens. The next generation of telescopes used mirrors to better focus light and improve image resolution at further distances. Built in 1934, the Palomar telescope reached the mirror size limit at 5 meters. In 1990, the Keck telescope broke that barrier with its 10-meter segmented mirror. Now that it has been 31 years since the Keck telescope, Fanson said it is time for the next doubling in telescope aperture. The Giant Magellan Telescope, or GMT, the 30-meter telescope, and the European Extremely Large Telescope are all underway to achieve that feat. The GMT will have a segmented mirror with computer control. The primary mirror will be composed of 7 individual mirror segments, each 8.4 meters in diameter. Computer control will allow the GMT to maximize image resolution by phasing the 7 mirror segments and correcting for atmospheric distortions with adaptive optics. Fanson said these advancements will allow the GMT to get near the level of imaging resolution that has so far only been available from space-based telescopes. The GMT will be constructed at the Las Campanas Observatory site at the southern end of the Atacama Desert in Chile. The remote mountaintop location means it has minimal light pollution, few clouds, and dry, steady air. The GMT will be housed in an enclosure roughly the size of a football field, with its operating machinery located in a separate building. Fanson showed an animation that gave viewers a tour of the completed telescope, highlighting its mechanical functions. Most modern telescopes are reflecting telescopes with primary and secondary mirrors. In the GMT, both the primary and secondary mirrors will be segmented, operating in pairs, arranged in the Gregorian optical design. These features together will be the first of their kind. Fanson then showed and described the process by which the mirrors are created, using 20 tons of E6 borosilicate melted in a spinning furnace. 5 of the 7 primary mirror segments have so far been cast and polished to a position of approximately 1/millionth of an inch. Once the mirrors arrive at their destination in Chile, they will receive a 200 nanometer thick aluminum coating and will be installed on the telescope structure. Each mirror will be affixed by 165 pneumatic actuators. GMT will phase the primary mirror segments by using the light from a guide star reflected off the adjacent edges of adjacent segments. Based on those dispersed reflections, GMT will identify the misalignment of the edges by the degree to which the interference fringes have rotated. A prototype of the phasing system has been in use on the Magellan Clay telescope at the Las Campanas site. Fanson then described the history of adaptive optics, first proposed by Horace Babcock in 1953, by which scientists can compensate for atmospheric distortion with actuators that can restore the reflected light to their original wavelength. Adaptive optics on the GMT will be accomplished by its segmented secondary mirror. Each segment will contain 672 actuators operating at 2 kilohertz bandwidth, allowing real wavefront refraction correction in real time. Once completed, GMT will have 11 instrument stations. Among them will be G-clef, an optical Echelle instrument that scientists will use to detect exoplanets, and 2 visible light spectrographs that can be fiber-fed to widen their field of view. Benson described the engineering techniques GMT will use to protect it from seismic activity and wind vibrations. He then described the current stage of construction and operations. He then concluded by answering questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:56 p.m., President Milstein adjourned the meeting. The temperature in Washington, D.C., 4.5 degrees Celsius. Weather, clear. Number of concurrent viewers on the Zoom and YouTube live stream, 118. And views on the PSW Science YouTube and Vimeo channels, 393. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to Corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. A video of the lecture is available for anyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and can be accessed directly from the PSW Science website, www.pswscience.org. We now turn to tonight's lecture. It is my pleasure to introduce tonight's speaker, Kate Kraft. Kate is staff scientist in the Space Exploration Group at Johns Hopkins University Applied Physics Laboratory. Previously, she was an aerospace engineer at NASA's Goddard Space Flight Center. A main focus of her work is developing NASA's Europa Clipper mission to Jupiter's icy moon Europa to investigate its geology, its geological activity, and its habitability. Kate is also working on several other projects for future landed and subsurface ocean world exploration missions, including a future landed mission on Europa. She is the principal investigator of a project to develop the communication technologies for future submersible cryobots, and she is working on microfluidic sample preparation devices for in situ purification and detection of chemical biosignatures, such as DNA, RNA, and amino acids. In addition to other honors and awards, Kate is the recipient of the JHU APL Heart Development Award, numerous APL IRAD awards for microfluidic sample preparation, a JHU APL Oscar Peer Award, and she was selected as Lewis and Clark Field Scholar in Astrobiology. In addition, she was one of 50 finalists out of 18,000 applicants in the 2017 NASA astronaut selection process. Kate earned a BS in Aerospace Engineering at Virginia Tech, an MS in Aerospace Engineering at the University of Maryland, and an MS in Geophysics at the Georgia Institute of Technology, and a PhD in Geophysics at Virginia Tech. All questions would be fielded in the Q&A session after the lecture. Kate, the screen is yours.
Okay, can you hear me okay?
Yes, we can hear you okay.
Great. Thank you so much for the introduction. I'm very pleased to be here this evening, getting to speak to you about this next super exciting flagship mission that NASA will be sending to the icy moon Europa, with an overarching goal to explore its habitability. Thank you for the kind introduction. Again, I'm Kate Kraft, and I'm a planetary scientist at the Johns Hopkins Applied Physics Lab. Okay, so Europa is one of the Galilean satellites of Jupiter. The Galileo spacecraft explored these moons from about 1995 to 2003, and it explored these moons as it did multiple orbits around the bodies there. Europa here is the second in the order as you move outwards in the orbital plane from Jupiter. Io is the innermost Galilean moon. It's very active, very volcanically active, and spews out sulfur as its volcanoes go off. And some of that material gets deposited on the surface of Europa. Europa itself is an icy moon. The whole surface of Europa is made of water ice. And then as you go further out, you get to the little bit larger moons, Ganymede and Callisto, which are also icy ocean worlds. However, their ice shells are much more cratered and much thicker. The ice shell to ocean ratio is much higher. So one of the really exciting things about the Jupiter system is that Jupiter has a really strong magnetic field. And as it throws out these magnetic forces in these fields, it can induce magnetism and a magnetic field in the other bodies around it. And so what was detected by the Galileo spacecraft was an induced magnetic field at Europa. And this is really what indicates to us that there is an ocean beneath the surface of Europa. That's a salty ocean. It's a fluid that is conductive and can induce a magnetic field at Europa. And we know it's a salty conductive material and it's a fluid material. And that's why we get this induced magnetic field. And this effort's been being led on the Clipper mission by the folks up here on the upper left. And the graph here that's being shown in the upper right can indicate to us how we can learn about a moon and its induced magnetic field, looking at the field strengths and how that relates to the ocean depth and also the conductivity. So we can learn a lot about the interior of these moons using this magnetic field measurements. So as Europa orbits around Jupiter, it's being pulled and tugged on. So Europa's orbit around Jupiter is not completely circular. It's actually slightly elliptical. And so that means some of the time it's a little bit closer to Jupiter, some of the time it's a little bit further away. And when this happens, as it goes around in its orbit, it's being pulled and tugged on, and it's being flexed. And so when it's being flexed, it actually causes some heating to be induced, both in the interior region and the rocky interior, and also in the ice shell. And so you can see here what we believe is happening with the tidal heating that's being induced in the inner regions of Europa. And the structure of Europa is such that it has an iron core at the center, it has a rocky mantle, and it has an ocean and an ice shell. Now, when you look at this ratio of these different materials in this small moon, and Europa is about the size of our moon, so it gives you some perspective on the size of this moon. It is looks like the ocean's not really that thick, but really this ocean we believe is about 100 kilometers deep, and so a very, very deep ocean with an outer ice shell that we think is in the range of a few tens of kilometers thick. So the ocean in Europa is about 100 kilometers thick, and we think about the small moon Europa being about the size of our moon. And so we thought, oh, there's not probably really that much water there. But when you combine the amount of water that's in that thick ocean around the inside of Europa with the water that's available on the surface of the Earth. So if we combined all the water from the oceans, the rivers, the lakes on the Earth, and we made it into a sphere, and we compare that to the amount of water at Europa, Europa actually has almost 2 times more water than all the surface water on the Earth. So it's a fantastic amount of water everywhere, right? As in the form of liquid as well as ice. We also think that due to that tidal forcing, that tidal heating, it could be inducing hydrothermal activity at the seafloor. So this hydrothermal activity is inducing chemistry and nutrients into the ocean, and it's also enabling that ocean to survive and to persist for long periods of time. Probably by now, Europa would have been just an ice ball if it had not been for this tidal forcing going on and enabling that ocean to stay at a temperature that can allow it to stay a fluid. We also think that this heating and this circulation that's potentially being induced in the ocean can allow the flexing at the ice shell to cause fractures and potentially enabling pathways for the fluid to make its way through the ice crust out into space, maybe as plumes or as eruptions onto the surface and flows on the surface, such as cryolavas. And we also think there's regions we call diapirs, where it's a warm, like more slushy type of material that over time oozes its way in a way up towards the surface and causes surface features to form on the surface of Europa. And what's really exciting about thinking about hydrothermal activity is when we look at the hydrothermal systems on our seafloor, back in the 70s, really not too long ago, right? We only just discovered these systems at our seafloor, where the warm magma near the seafloor is inducing seawater to circulate, bring chemistry up to the ocean water, and form these chimneys, these black smokers. And here we see life. Here we discovered life that only has to live off the chemistry at the seafloor. It does not have to have light. We used to think that all life needed light, sunlight, but now, this really opens up the world of possibility for what other worlds might be able to harbor life. If these icy ocean worlds that are not open to the sunlight above can potentially harbor life down here that can just live off the chemistry, this really opens up just so much more potential for life in our own solar system. So when we look at Europa's surface, it's a cold, icy moon. It's about 100 Kelvin at the surface, and which is about negative 173 Celsius. Really cold at the surface, heavily irradiated from Jupiter's strong magnetic field. We see all kinds of really interesting features. We see reddish material that's a composition that's a combination of salts and sulfur that's been deposited from Io and irradiated over time. We see structures, long linear ridges. You can see over here the ridged plains where we see these features that are called double ridges, which look somewhat like the double ridges on our seafloor where the new magma is coming up. But here it could be like a long linear fracture traveling for thousands of kilometers, some of them do. And these raised ridges on either side. We see fantastic regions called chaos terrain, where these blocks are jumbled and have been turned onto their side. They've broken. You can see remains of the ridges that used to crisscross across their surface. This is indicative potentially of near subsurface water. We do see a few craters, but actually the interesting thing about not seeing that many craters really indicates to us that Europa's surface is very young. Most of the other moons, as I mentioned, Ganymede and Callisto, they're very heavily cratered, which means they're an older surface. And so Europa's surface is theorized to be about 50 million years old, so really geologically young. We also see these really interesting little spots on Europa, which are called lenticulae. And we like to call them freckles on the surface of Europa. And these are, some of them are domes and some of them are pits. And so we're not really sure how they formed. Maybe they're warmer material that's come up near the surface, or potentially even cryolava flows. So here we're going to zoom in on a double ridge on Europa and just get the perspective you might get if you were on a spacecraft flying in to investigate and get a closer look. And so you can see how in the middle there's this fracture that's running along the middle with these raised double ridges on either side. Many other fractures, previous fractures that are crisscrossing all along, running alongside. In some of the double ridges, we see flanking subparallel fractures that may indicate a nearer thermal anomaly nearer the surface that's allowed flexuring of the surface to occur. Another really interesting feature that we see on the surface of Europa are called bands. So these are regions on the surface that are smoother, that may have some ridging going on, multiple ridging along their surface, but they're regions at the surface that have been theorized to have been formed by warm material. As the surface maybe has spread apart, this warmer convection that may be happening deeper down in the ice shell is allowed to bring this warmer material up towards the surface and form these areas we call bands. We also see regions that have been termed subsumption zones. And so these are areas where actually we see, whereas bands have brought up potentially new material, we see regions of the surface that may be missing. And so this indicates that some of the material may be actually being subsumed into the cold ice shell beneath. And so it's somewhat similar to on Earth, where we have subduction zones, where plates are moving across on top of one another. Some of the material is being pushed downwards beneath the upper shell. And then speaking a little bit about the craters that we see on Europa, are that we see some larger features, which are multi-ringed crater basins. Here is Tyre, and the above one is Callanish. And we also see smaller features that have some of the material in the center that's been raised, the raised center point of a crater. And then some are you're barely even able to see evidence of where they entered the ice shell. And this can help us learn a lot about the ice shell structure at these locations. And then, of course, we want to study the composition of Europa. You know, currently what we know about Europa is that there's salts on the surface. Many of them have been irradiated. There's a lot of lab experiments that people are doing to irradiate different kinds of salts to try to understand what the colors can tell us about what we observe on the surface of Europa, what that might indicate for different compositions. And it's really exciting to see evidence of salts, because that means there's potential that this ocean material has come to the surface and deposited on the surface. We also see evidence of sulfuric acid and sulfur. So the sulfur coming from Io and being deposited is being irradiated and maybe turning into sulfuric acid, which could potentially pose some challenges for future missions that are trying to study and sample there. Again, ice shell convection may be a source of bringing material towards the surface. So if you can remember back in the day when we had lava lamps around and how the material flows upwards, and that's a heat motion of being in density difference. As you warm things up, they will move around and change places due to the density. And so this convection may be happening deep down in the ice shell and maybe allowing material to flow and move around, and potentially could be a source of mechanism to bring a material to the surface at these freckle pits and domes locations on the surface. And then again, the chaos terrains. The chaos terrains, there's one here, Connemara and Thera up here in the upper right. And these are just regions of jumbled material, material that has somehow been allowed to move around, turn on its side, flip over. And we see these kinds of similar types of features in the polar regions on Earth, where the Arctic and the ice shell has been allowed to break off, pieces break off, and they get all jumbled and move around. And this really can be indicative of near surface water beneath of those ice blocks that allow them that motion to be able to move and turn around. So this has been theorized to be a potential source for allowing this material at the surface to move around. And so these, of course, are one of the places that Clipper we hope to make great observations at, hoping to find evidence of near subsurface water. There are also some of the younger features on the surface. And then, of course, plumes. Plumes are really exciting for many reasons, but one is that potentially that's material that's coming directly from the ocean, right? If we're able to arrive at Europa and see plumes happening and we fly through them, we'll be able to, you know, sniff and smell and taste the potentially directly the ocean of Europa. And so we're not sure. There's been some observations that are intriguing of potential evidence for plumes. They haven't been repeatable or observed again in these locations of Europa's orbit where we would expect maybe to see them if they were somehow driven by a periodic process. But still, we are very intrigued about looking for these with our mission and hope to see some. So with all of that, you know, Europa is this exciting world, but really to understand, you know, is it habitable? Does it have the ingredients that can support life? We need to study certain things about it. We need to really understand the water, you know, how much is there? How salty is the water? You know, we can use the magnetic measurements and thermal models to help tell us about that. The possible lakes within the ice shell, are there places where maybe the water doesn't get all the way to the surface, but it gets near to the surface? The chemistry of this world, is the ocean in direct contact with mantle rock, which would allow it to promote this chemical leaching, bringing chemistry from the rock into the ocean. The dark red surface materials on the surface of Europa, what exactly are those? You know, what salts are present? Are they from the ocean? The energy that's available. Life needs energy, the chemical energy that could be supplied by the hydrothermal systems that could sustain life. Surface irradiation actually helps. So in this environment where it's heavily irradiated, life doesn't want to hang out on the surface. You know, that's really a bad place for life to be. But the process that it's undergoing of the materials at the surface can produce oxidants. And then in combination with the reductants that may be being produced by the hydrothermal systems, if they're allowed to mix the oxidants and reductants, that really provides an environment of which is conducive for life. So Europa Clipper will go and investigate Europa for all of these reasons. Overarching is the goal of really understanding and being able to characterize its habitability. It'll do this through certain science objectives. We want to study the ice shell and ocean. We want to characterize those areas, really understand how much subsurface water is there any in the ice shell, understand the ocean properties, its salinity and conductivity, what is the nature of any surface to ice to ocean exchange? You know, is there any exchange processes going on, or are they fairly separated? Composition, understanding habitability requires us to understand what materials are there, what kind of food is there for life to eat, and the exchanges there as well with the different compositions and how that could provide the right chemistry and environment for life. And then studying the geology, understanding how those geologic features form really helps us understand how Europa works, like what are the mechanisms that are occurring, and can help characterize for us what sites, if we want to land there in the future, what sites really are the most scientifically interesting, where is the water really the closest to the surface that we might potentially sample it. And so part of Clipper's mission is to also, you know, seek out sites of high science interest and also safe landing sites for a future lander. And any recent activity, if we can see evidence of plumes, if we see evidence of changes on the surface between flybys or between what Galileo data has images of previously, and compare it to what Clipper gets, and we can see if there's any evidence of recent activity. So the suite of instruments on the Clipper mission include all that you see here. We have a couple groups of remote sensing instruments as well as in situ. And the remote sensing instruments are the ones in blue, circled in blue, and the in situ are circled in gold. And so I'll just speak quickly through the different ones that we have. And this first one here is mass specs. It's a mass spectrometer being led by Jim Burtz at the Southwest Research Institute. It'll sniff the atmospheric composition. We have a SUDA dust analyzer being led by Sasha Kemp at the University of Colorado, and it will detect surface and plume composition. The Europa Clipper magnetometer being led by Margaret Kilvison of the University of Michigan, which will go after revealing the ocean properties. The PIMS instrument is a plasma instrument that uses Faraday cups and is being led by Joe Westlake out of the Applied Physics Lab. It'll measure the plasma environment. And then the gravity and radio science is the other in situ instrument, which will use Doppler gravity measurements to interrogate the ice shell and overall moon structure. And it's being led by Erwin Mazarico out of the Goddard Space Flight Center. And then we have remote sensing instruments. So the Europa ultraviolet spectrometer is being led by Kurt Rutherford at the Southwest Research Institute, and it'll seek plume glow. And I'll speak more in detail to all of these in the following slides. But the ICE, as the Europa imaging system, includes actually two cameras, a narrow angle and a wide angle camera. And that's being led by Zibby Turtle out of the Applied Physics Lab. And it will do all the imaging of the surface of Europa. The MISE instrument is an infrared spectrometer being led by Diana Blaney out of the Jet Propulsion Laboratory. It'll detect chemical fingerprints and the composition at the surface. The e-Themis instrument is a thermal imager being led by Phil Christensen out of Arizona State University, and it'll search for hotspots. So really give us a good idea if there's any liquid water coming near to the surface. And then REASON is an ice penetrating radar. This really interesting instrument is going to be able to interrogate the ice shell, look for water pockets, tell us where that ice-ocean interface is. And that instrument's being led by Don Blankenship out of the University of Texas Institute of Geophysics. So I'm going to start by going through our remote sensing investigations. So again, I'm talking a little bit about what we already know about Europa plumes. We've had several independent methods of detection that point to the existence or the potential existence of plumes at Europa. We've had ultraviolet and thermal imaging, radio occultations, magnetic perturbation measurements. So there's been several studies that are listed here. Roth et al. In 2014 took some line emission measurements and looked at dissociation products of water. The Sparks et al. Study looked at off-limb continuum absorption as Europa transited Jupiter. And the Jha et al. Looked back at Galileo data and the ionized plume particles that were interacting with the incident plasma, causing slowdown and flow diversion of the magnetic field. And so these are ways that we've been searching for plumes at Europa. A lot of these measurements have sort of been at the very edge of the measurement capabilities, and that's some of why we're only calling them putative observations, not yet confirmed, but we're looking very much forward to confirming those with Europa Clipper and further searching for plumes. And one of the instruments that will achieve this is the Europa Ultraviolet Spectrograph. And it's the Europa UVS instrument. It will seek to interrogate and characterize the atmosphere. It'll look for plumes. It'll search on the surface for the composition and microphysics and relate those to what's happening endogenically versus exogenically. So what's happening at Europa or coming from Europa and what's coming from outside. It'll also interrogate and investigate the plasma environment. It'll investigate energy and mass flow into Europa's atmosphere and neutral cloud and plasma torus. It'll do all this through spatial and spectral UV imaging. The high spatial resolution mode allows for imaging of the detailed surface and plume structures, and it'll perform solar and stellar occultations to determine composition. So this is where it looks from far away, and it looks as Europa transit past certain stars, and it'll use that to look for this information. And we're in the phase right now that Europa is in, we're actually starting to put CAD drawings, engineering drawings to hardware. And so it's in a very exciting time for the mission right now, where we're actually starting to build engineering models and flight hardware, really getting ready to launch in only really a few years. And so here you can see what was originally the original design for the instrument, and now some hardware pieces that are being put together. The key instrument parameters are listed here, and I won't go through all of them for the instruments, but if we'd like to go back, we can do that later. Okay, so the Europa imaging system is the set of cameras that are going on Clipper, and they will help constrain the formation of surface features and potential for current activity. So they'll be looking for plumes as well. It'll characterize the ice shell and characterize the surface regolith at small scales. Those two instruments include the narrow angle camera, or the NAC, and the wide angle camera, or the WAC. And the narrow angle camera gets the highest resolution. It can also do stereo imaging and in color. NAC has a gimbal. So the NAC instrument, contrary to most of the other instruments on the Clipper mission, can actually turn and look in different directions. It doesn't always have to be looking nadir as we fly by Europa. So it has this extra capability. It enables it to have some independent targeting, and it also enables to do near global mapping of the surface of Europa, and also in stereo, and also do high phase observations to search for plumes. The WAC looks along track as we fly over Europa and can also do stereo and color imaging. WAC supports cross-track decluttering for the ice penetrating radar. So when the radar is doing its sounding and its reflections, it sometimes, has to be, it can't tell on its own if it's looking at something in the subsurface or if the reflection is coming from either side. And so the WAC imaging actually helps them determine whether the signal that they're receiving is coming from the subsurface or from a further distance to the side. Here's just an image that we can use to show how well the WAC and NAC can get images. So here is a region of Europa's surface at the 10-kilometer scale bar here, and we start to zoom in using the different cameras. So this region here is now the WAC at color. You can zoom in on it and get color information at less than 500 meters per pixel. And then moving to the smaller yellow square, we zoom in with the NAC and get global mapping at less than 50 meters per pixel. And then zooming even further in on this very small region, we get NAC high-res stereo and imaging at 0.5 meter per pixel at the 50-kilometer altitude. So the resolution just continues to get better and better, as we get closer to the surface on our flybys. The Europa thermal imaging system will also detect and characterize thermal anomalies that may indicate recent activities such as plumes. It'll help us determine if we see evidence of plumes, where those plumes may be coming from. And also it'll characterize and determine the regolith particle size, any blocks that are around, and subsurface layering for future processes studies. So it's, when you're trying to figure out how a geologic feature was formed, all this information is really important. And then when you think about places that you might want to land, understanding how many boulders might be around is also very helpful for avoiding any unwanted tipping over of your lander. So looking for regions that are more, have less boulders, smoother regolith would be ideal. And so this type of information will also be very helpful to future landed missions. The instrument itself is has high capability for high resolution thermal images. It takes images both at day and night, and that's important for understanding thermal inertia. It uses an uncooled microbolometer array with 3 spectral channels, and it has time delay integration for measuring very low temperatures. The MISE instrument has the ability to assess Europa's habitability by understanding the inventory and distribution of compounds. So it really looks at the composition of Europa's surface. This also helps in understanding Europa's geologic history, and it will search for areas at the surface that are currently geologically active. So by being able to identify organics and salts, any hot spots and ices, we can further understand when geologic activity occurred, where its sources might be, so where that material may have been sourced from. So it's a spectrometer that you get reflectance data from, and you use that to understand what materials you're observing. So we can see evidence of water ice, different types of salts, benzene, octane, different types of compounds. And this can tell us a lot about the salt and ice chemistry, as well as making detections of trace organics. The REASON instrument is the ice penetrating radar. And this instrument will characterize the distribution of any shallow subsurface water. It'll search for evidence of ice-ocean interface, the ice-ocean interface here at the base of the ice shell. How thick is the ice shell? How thick is the ocean? It'll help us understand that. It'll also characterize the ice shell's global thermophysical structure. It'll look for evidence of material exchange between the ocean, the ice shell, the surface, and the atmosphere. It'll constrain the amplitude and phase of the tides. So again, if we recall that as Europa is going around Jupiter, it's being pulled and tugged on, and the tidal forcing actually can cause bulging of the surface. And so it will help identify how much bulging is occurring, which can be indicative then of how thick the ice shell is. It'll characterize scientifically compelling sites and hazards for a future potential landed mission. And so the Reason instrument uses two different frequencies for its radar. It has a high frequency radar at 9 megahertz that can penetrate more deeply into the ice shell. And so that's the frequency that will be used to try to get at determining where that ice ocean interface is. It also uses a very high frequency, 60 megahertz, to probe the shallower ice shell. It also uses reflectometry and altimetry to get at the tidal forces and bulging, and then also just interrogating the ice shell for fractures and water pockets. So if we were to lay the fields of view of each of these remote sensing instruments upon each other, I can show you here how they kind of nest within one another. So the along track direction is going from left to right, or right to left, either way. But if we're going, say, from left to right here, the along track is in that direction, and the cross track would be in perpendicular. So the along track and cross-track fields of view are shown here. So the gray box is the field of view of Reason out at 60 degrees. And then the nested one inside of that is the ice WAC, which has a 48 degree by 24 degree field of view. And then inside of that is the Europa UVS field of view here in yellow or gold. And then the E-Themis field of view is more like a line, and it can be a long track as far along as the observation is performed at. Then within there is the MISE field of view here in red, and the innermost being the NAC, the ice NAC. And the resolution of each of these observations is shown here for an altitude of 100 kilometers. So at 100 kilometers, UVS will get 35 meters per pixel, WAC will get 22 meters per pixel, NAC will get 1 meter per pixel, MISE 25 meters, and E-Themis 20 meters per pixel. Okay, and then moving to the in situ investigations. So starting off with talking about, again, just a little bit of background about Europa's induced magnetic field. So the magnetic field allows us to really understand better the subsurface ocean, to determine its location, thickness, and conductivity, and salinity, if we can get compositional information as well. And then due to Jupiter's tilted dipole magnetic field, this allows us to get information about the interiors of these moons, because that tilted dipole magnetic field induces eddy currents in the ocean, which can be measured. It's also inducing a magnetic field at distinct periods. So it has an 11 period, an 85-hour period, and shorter harmonic periods. And we can use these distinct periods to also gather more information, as can be shown here in the right most figure, where the blue line is showing the 11.2-hour period, and the red line showing the 85.2-hour period. And using those measurements and induced field responses, this allows us to both get at ocean thickness and ocean conductivity, as well as ice shell thickness. So the Europa Clipper magnetometer, shown here, is the instrument that will focus in on making observations of this type. It'll help determine the location, thickness, and salinity of Europa's ocean. It'll also characterize any active vents, plumes, and ionized plasma trails. And it'll help us understand the coupling of Europa to Jupiter's ionosphere, and then also coupling of plumes to flowing plasma. So the instrument itself is a 3 flux gate magnetometer. So there's 3 of these flux gates on the end of the boom here, and it's an 8.5 meter long boom. So it has to extend these sensors away from the spacecraft to prevent them from measuring anything that's being induced by the spacecraft. And so that's why you'll almost always see magnetometers kind of stuck out on a boom way far away from the spacecraft. But these flux gates are what are taking the measurements. And we also have to do in-flight calibrations and spacecraft rolls that require spacecraft rolls. We have to do about a roll on every third Europa encounter, or several rolls on every third Europa encounter. Here's a actual piece of hardware that's being built. We have these 3 flux gates and the interior, the model of the interior for how it works. The PIMS instrument, the plasma instrument, will also look at magnetic field. It's going to determine Europa's induced magnetic field response and help correct for any plasma contributions in order to estimate ocean salinity and thickness. So actually the PIMS instrument and the Europa Clipper magnetometer will actually work together to try to get at ocean salinity, ocean thickness. The PIMS instrument will also help understand the mechanisms of weathering and releasing material from Europa's surface into the atmosphere, and will help us understand how Europa influences its local space environment and Jupiter's magnetosphere. The plasma near Europa has a strong contribution to the observed magnetic field and masks the induction response from the subsurface ocean. And so this is an important reason why PIMS and Europa Clipper magnetometer work together to get at the question of salinity and ocean thickness and things. To the right here, you can see one of the sensors for the PIMS instrument. There's 2 of these on the spacecraft, and each of them has 2 of these Faraday cups. And they're each positioned at 90 degrees to each other. These instruments measure the ion density, temperature and velocity, electron density, and temperature. The sensors, thankfully, these sensors are immune to the degradation and background noise from radiation. And so they're ideal for use in this environment. So speaking of Europa's radiation environment, there's a lot that we don't yet know about the radiation environment. We have several models that can indicate to us which parts of Europa are more heavily bombarded by the radiation of Jupiter. And yet there's a lot we still don't understand. And even though the Juno mission has been there and is in the Jupiter system currently, it hasn't yet done very many flybys in this vicinity of where the Europa Clipper mission will be going. However, it's very exciting because we do know that just recently the Juno mission has had an extended mission approved, and they will be doing a few flybys of Europa. And so we're hoping that those flybys will get great pictures of Europa, but also help get further information about the radiation environment that we can use in our models to further understand of how our spacecraft may be affected by the radiation there. So we do have a radiation monitor, which is it's on an engineering instrument, and it's being built at the Applied Physics Lab. And this will help us understand Europa's radiation environment and its effect on the surface of Europa. It's basically going to take these measurements using a charged monitor stack. And there's 3 plates here that are of certain thicknesses, and each of those plates provide a crude energy spectra. So each plate makes observations or has impacts of energy on their surfaces, and this energy absorbed then translates to the energy transmitted. These instruments are used in combination with dosimeters, which we have about 8 of dosimeters shown down here in the bottom right. We have about 8 of those distributed around the spacecraft, plus also hosted inside of science instruments. And each of those will return integrated radiation flux above an energy determined by local shielding. So we will use these to measure the radiation that's being experienced by both the spacecraft and the instruments during the mission. And these instruments are building off of heritage of Van Allen probe's radiation monitor. The gravity and radio science investigations will really help us understand Europa's structure and any time-varying gravitational tides that are occurring at Europa. It will help confirm the existence of the subsurface ocean, and it'll help constrain the ice shell thickness. So basically, the gravity science investigation uses the transmission of signals back to Earth and uploading from Earth to understand how the spacecraft's trajectory changes as it passes by Europa. And based on those trajectory changes, it can tell things about what the density and what the materials are within the moon. and the thicknesses of those materials. So it uses 3 fixed fan beam antennas plus 2 low gain antennas to fill in the coverage that it needs during those flybys. And here you can see the field of views of those different antennas. It also uses the high gain antenna, which is a big circle here in the middle, for occultations and Io plasma torus measurements. And that's the plasma that's kind of following along with Io in its orbit, and it passes the transmission of the signal through that to basically calibrate that plasma effect out from its transmission observations. And the radio science receivers use the Deep Space Network for transmission, and will also potentially being used some European Space Agency antennas. And this is a non-intrusive investigation with a suite of science instruments. So it's not competing with any of the science investigations and can be used at any time. So the Europa atmosphere is really not much of an atmosphere when you think about like Earth's atmosphere. It's more of an ionosphere, where an exosphere, a very low on density of material. But there are materials there. There's abundant species of water, hydrogen, oxygen, carbon dioxide. There's also likely organic compounds. And so it's going to be really interesting for us to try to characterize the distribution of these volatiles and any key organic compounds. High mass resolution data of these measurements will enable us to get at individual fragmented ions generated by electron impact ionization. So as the high radiation and high energy particles are impacting the surface of Europa, we can make measurements of the particles that come back off. And measuring low abundances requires extensive contamination control of our spacecraft. So when you think about these in situ instruments that are collecting these particles as we fly by Europa, if there's any particles coming off of our spacecraft that we haven't well characterized, that, quote, contamination, we don't want to be measuring things that are coming off the spacecraft. We want to be measuring the materials that are at Europa. And so it's really important to keep our spacecraft clean and not be worried about materials coming off the spacecraft, it can be challenging when we're in this high radiation environment. But we've been working to characterize any outgassing materials. So the instrument that will really focus in on doing these measurements is the mass spectrometer and mass specs. And it's going to help determine the distribution of these major volatiles and any key organic compounds in Europa's exosphere and any plumes that we come across. It'll also determine the relative abundances of key compounds to constrain the chemical conditions of Europa's ocean. It uses a multi-bounce time of flight mass spectrometer. And so you can see this picture here, of the mass spectrometer. And inside there is where the particles will bounce around and the time of flight will be recorded, and that will help determine what the particles are made of. And it also uses region of interest scanning for high resolution over a broad mass range. And that mass range, again, is this mass range here, where we're looking to see what mass range are we getting indications of materials, and that will tell us what composition of materials we're looking at, making observations of. The mass specs also has a cryotrap that allows it to capture material, keep it at really cold temperatures, and then wait for the spacecraft to get back out at periapsis where it does the measurement then in the low radiation environment, like outside of Jupiter's high radiation. Also of interest is Europa's cosmic dust environment. So there's also a lot of dust material that's being impacted. So the surface of Europa is impacted by micrometeorites, and it kicks up a lot of dust. And that material floats around for a little while before settling back down. And this material can be sampled. And so the dust particles are expected to be about 0.5 to 1 micrometer in size. They're ejected by these hypervelocity impacts of micrometeorites. And the distribution is near isotropic with no strong temporal variations that's been measured so far. And so some variations are due to the orbital motion of Io, and also Io has those volcanoes that are periodically going off. And so that material is not a constant flux. It's kind of stochastic in nature. And so the ejecta is off the surface combined with material that's coming in exogenically can be measured. And it's a process of trying to understand what's endogenic versus exogenic. But the measurements will look for salts, salt hydrates, complex organic species, and silicates of exogenic and endogenic origin. So the main instrument that'll go after this information is the SUDA instrument. It'll map the surface composition of Europa. It'll characterize the alteration of Europa's surface compared to the exogenous dust. And it'll also determine the composition of the particle matter in active plumes. So here on the right, we can see some pictures of real hardware being built. Here we have the schematic of how it works. It has an incoming particle that passes through and bounces back into the sensor in the middle. And here that particular cup and detector is shown here at the right. We also have a sensor head, lab prototype, and the iridium coated target. It's a time of flight mass spectrometer, and the composition of the particles ejected from the surface can be correlated with the geologic features. So they're actually very interested in collecting material over certain geologic features, because then we can use the information about that material to help us understand how those features on the surface were formed. It'll also look for trace amounts of complex organics, and they could be detected in ice grains at better than 0.1 parts per million. So here's just another picture of some of our fantastic hardware being built for Europa Clipper, where you can see the MISE Flight Dyson calcium fluoride lens here for the MISE instrument. We have an E-Themis flight model telescope housing, the PIMS flight controller assembly, the SUDA engineering model in the dust chamber, an ECM Pathfinder, that's the little sensor for the ECM for the magnetometer, Europa UVS flight model housing, the ICE NAC engineering model, the mass specs engineering model here. And then here is the deployment of the Reason very high frequency prototype. So I'll play this real quick. So that actually just releases and springs outwards. So how will we fit all of these instruments on our payload? We have a lot of fantastic instruments, and we got to get them all to fit, and we want them all of the instruments looking in the same direction. And in this way, we don't have to sort of make decisions about who's going to get to make, which investigation gets to make an observation that pass. And so by having all of these instruments looking that need to be look in a certain direction, it allows us to both not have to worry about resources as much, and be able to also get multiple types of observations at the same places on the surface of Europa. And this will really help us just get at these questions that we have about how features are formed, what's the habitability of Europa, what's the composition, and how all those different pieces fit together to get at the answers of our science questions. The Europa Clipper spacecraft, shown here at the left, is we're being powered by solar panels. We have 5 panels on each side of the spacecraft. That's about 5 panels is about the length of a basketball court, and so they're pretty big. And they fold outwards. After we've launched, we have also this 3-meter body fixed high gain antenna. Again, we have an 8.5 meter Clipper magnetometer deployable boom. It's a spring deployment, so it just coiled and springs outwards with the 3 flux gate sensors out at the ends. We have Reason high frequency antennas. So there's one on this side and one on the opposite side. And we have 4 of the very high frequency radar antennas, which can be seen here. And that's what the little video deployment was that you saw. And then we have the in situ instrument deck here, which is pointed RAM during flybys, and then the remote sensing instrument deck, which is pointed nadir during flybys. The nadir is just pointing down at the surface as we do our flybys. So currently, our most recent trajectory, we do trajectory assessments like periodically during our mission development. And the most recent trajectory assessment that we've done is a Mars Earth gravity assist. So this trajectory has us launching in October of 2024 and doing a flyby of Mars, then swinging back and doing a flyby of Earth, and then swinging out all the way to Jupiter. And this time of flight will be about 5.5 years to get us out to Jupiter. One thing that's really great too for our spacecraft for this type of trajectory is that we will only have to go in towards the sun as close as 0.82 AU. And so this is much more favorable for our thermal design, because when you think about designing your instruments and your spacecraft to survive out at the really cold temperatures of these outer worlds, to have to also survive when you going closer into the sun is very challenging. So by not having to go as close in to the sun, it's very helpful. The Europa Clipper mission will do about 40 flybys. And I apologize, I can't, okay, now I can. Okay, so it has about a 3.5-year prime tour and has more than 40 flybys. And during this time, we have a maximum of 4 mega rads for our radiation dosage. And so you'll see that we don't actually get up to this level during our prime mission, which allows us for some flexibility for a potential extended mission. But as we do the flybys, as the video shows you the flybys, you'll see the colors change, and that'll indicate at what level radiation we've gotten to. And so we're doing multiple flybys or swinging and getting closer and closer. And then we start to do multiple flybys of Europa. You can see here. Okay, and so it does, rotate around with time, and it moves a little bit, but it's mostly kind of going in the same spot. And during the beginning half of our mission, we're flying on the anti-Jovian hemisphere. So we're going to fly on the anti-Jovian first, and then we're doing a change here to go around and switch to doing flybys of the sub-Jovian side. So the sub-Jovian side is slightly more challenging. It's more radiation there. And so we'll do the anti-Jovian first, then switch over to doing the sub-Jovian. And then we'll complete our 45-ish or so flybys and end the prime mission. So the strategy for operations of our mission is to do simple, repeatable operations. So we've set up this structure such that we have similar observations being done for every flyby, so that it's simple and repeatable. There is flexibility, of course, in there for plume observations that are more further out, looking across the limb for plumes, or stellar occultations and things that can happen further out from the flybys, but the flybys themselves are fairly fast and need to be simple and repeatable. And so by doing this, we really simplify operations and can have the quicker flybys as we need. So flybys will occur about every 21 to 14 days, starting out with the longer flyby period, the longer period between flybys, so that we can get our feet under us as we start to orbit Europa, or orbiting Jupiter, doing flybys of Europa, and understand better the environment that we're having to function within. And so the way that works here is that the closest approach minus 2 days begins our encounter, what we call an encounter. So 2 days out from passing our closest approach begins our encounter. We approach Europa. When we turn the spacecraft and all the instruments pointed nadir, we pass our closest approach, and then we have our departure. And then as we depart, we're also doing a couple engineering activities such as reaction wheel biases, and then orbital maneuvers to keep our orbit where we want to pass Europa for the next round. And so we also do calibrations at certain points. And also here is denoted the mass specs cryoanalysis. And that's where I mentioned that mass specs can hold on to a sample that it collects at Europa and then process it out at apogee. So it's out of the high radiation environment. And during this time, we will play back data. The current mission design consists of more than 40 of these low altitude flybys and has a duration of about 3.5 years. Here's showing a map of the ground tracks. So, and the colors denote how close the spacecraft is as it passes over this region of Europa's surface. So you can see here that the 180 degrees west longitude indicates we're on the anti-Jovian hemisphere. And then we do a switch and we start to fly over the 0 point, which is the sub-Jovian point, and we do flybys across that hemisphere. We will range in altitude from 400, the highest from like 1,000, 400 is just when we start to show the ground track here. Some instruments can make observations from higher altitudes, but from 400 or from 1,000 down to 400 and switching to green as we get down to 100, then going to 50 to 100 kilometers, and then 50 down to 25 being the closest that we ever get to the surface is about 25 kilometers. So how will we return all of this fantastic data? Well, we're going to get a lot of really great data, and we have to have a way of considering how best to get that all returned. So we have a way of sort of prioritizing the data, and these are all decisions that are really made based on a few factors. One of them is being this decisional data of the highest priority. So any kind of data that an instrument really needs back very quickly to assess, you know, how well is the instrument functioning? Is there anything that needs to be changed with the operations so that the next time, the next flyby, it'll be able to do a better observation. You know, this will be very important, especially in the very first few flybys, as we really understand how the radiation is affecting the instruments. Then we move to encounters where the volume of the data that's being downlinked is valuable to get back before the next encounter. And so this data is prioritized to be returned before the next encounter. Then we have the mission level data, which is only downlinked, just said, oh, as long as we get this back before the end of mission, we'll be happy. And then opportunistic data is downlinked as if time is available. So it's put and it's stored, but only downlinked if there's opportunity to do so. Now, really a lot of the decisions about what is needed down for encounters is really tried to be done from the science perspective. So we're attempting to move away from, you know, my instrument and I want my data to what does the team need? What do we need? What kinds of data do we need to answer our science questions? You know, we need really a lot of different types of data oftentimes to really answer the questions that we're after. And so by prioritizing the data based on our science and our science questions rather than one particular type of science is really the overall one team philosophy to get at the best science possible to get this mission to return the best science possible. So this image shows you our web of flybys, as we like to call it. And so with similar coloring, just that the highest altitudes are shown in white rather than black. And really shows you, how we're really getting mostly at the subjovian and anti-Jovian hemispheres, not so much the leading and trailing hemispheres, but these two regions of Europa. But still, actually, when you look at the maps of coverage by our different instruments, you'll see that especially, for the cameras are going to get at 80% or better coverage of the surface because they really can, with that NAC, with that narrow angle camera, it can get great images still from pretty far away. Reason gets great coverage over the ground tracks of the subsurface. Themis gets potentially almost global coverage for day and night coverage. Europa UVS, which is getting at potential plumes and different compositions, gets pretty full coverage, as well as MICE, which again is getting compositional data across the surface of Europa. Okay, so this next animation is going to take you on a ride on Clipper. So we're going to fly into Europa. We're going to look at which instruments are being turned off when and making different observations. We'll see here in the upper left what the altitude of our spacecraft is as we fly by Europa. And you'll see the flyby speed as well. And then you can also see in the bottom right where we are in Europa's orbit, or as we're flying by Europa and Jupiter, around Jupiter. So I'll just get this started And I'll talk to you a little bit as we're going by. So you'll see the spacecraft maneuver a few times as it adjusts. A lot of times it has to adjust for what's best for the solar panels. And so it does then a rotation to get now in line for the instruments to make observations of Europa. So it's taking some observations from far away. Most of these observations can be done without spacecraft maneuvers, but then you'll see a few that do require the spacecraft to turn and do scans. So imaging, another spacecraft rotation. The orange there is the e-Themis taking full global imaging. There's a full spacecraft scan, so it actually rotates the spacecraft. Coming in, doing some imaging. So now things will start to move more quickly. You'll see as we get closer and closer to the surface, take a lot more observations, rotation of the solar panels, they rotate and then they stay still for the final encounter period. So Reason can take its data because Reason again is on the solar panels. Okay, so quickly go by Europa, taking lots of fantastic data, doing more on the way out. Okay, and then here's some images also of the spacecraft hardware that's being completed as we speak. We have a fantastic high gain antenna being produced here. The nadir deck is being machined where all the instruments will be attached. We have the stacked propulsion cylinders, which I think are undergoing testing right now at the Goddard Space Flight Center. Just a lot of fantastic hardware coming to fruition as we move closer and closer to launch. This is, a little nostalgic. It's our last in-person planetary science group meeting that was held at JPL in February of 2020. We have a strong team of a diverse group of people, engineers and scientists who've all come together to make this mission possible. You'll see here in the center our special guest of honor at every one of our meetings. We have a monolith that participates in every one of our meetings. Just a nostalgic Europa symbol. So I encourage you to go to the europanasa.gov website to find out more about the Clipper mission, but I'm not going to quite stop here. I'm going to take us even further, what could be to come after Europa Clipper. So in the future, we also hope that we will go and land on the surface of Europa. I've been participating in a Europa lander mission concept study where we've been investigating what we could do to really interrogate the surface, take samples, interrogate those samples, and look for signs of life. So the mission concept here is that we would land, we would collect at least 3 samples of about 7 milliliters each, and we would perform analyses on those looking for biosignatures. We'd also perform geophysical and visual observations to get at the contextual information and further determine how habitable Europa is. So you can see here the product of the science definition team where we scoped out different instruments that would get at these high level goals for really assessing both signs of life, how habitable Europa is at the landed scale, at the near subsurface, and context for that information. So we have a gas chromatograph mass spectrometer, a microscope, a Raman spectrometer, and context cameras to get at signs of life. And then adding to that set, we would add a seismic package for getting at habitability and contextual information. I can encourage you to go to this website here to get more information where there was a really great SDT report that goes through all of the background and reasoning for coming up with the instrument suite as well as the goals of the mission, and also goes into a lot of the engineering details, including how exactly we would land. So I hope a lot of you saw the Perseverance landing recently, where we got to actually see a lot of fantastic imagery of the actual sky crane as it lowered the Perseverance rover down. And the Europa lander mission would be a very similar concept. We wouldn't need a parachute. There's no atmosphere on the surface of Europa and at the surface or in the region of Europa, and which actually kind of simplifies things a little because we don't have to worry about wind blowing us around at all. We just come in to land with our thrusters on, and we get lowered down to touch down softly on the surface of Europa. And this is an image here showing how the concept goes about thinking about how we would cut into this hard, right? This ice is very cold. It's almost like rock, and you're cutting into that subsurface and scooping up sample and bringing it in for scientific analysis. I've also then been participating in, or also previously participated in a study thinking about how we could send a cryobot down through the ice shell of Europa, reaching the ocean. And so the technical objective of this type of mission would be to reach the ocean or a subsurface water pocket or a lake that we could reach maybe in the range of 4 kilometers or so below the surface. So in studying this, we also came up with several scientific goals very similar to the Europa Lander Science Definition Team report, where we would look for evidence of life, assess the habitability in situ in the ice shell, as well as the ocean once we reach the ocean, and characterize the surface and subsurface properties. And so following on from that study, I was funded to lead a team to think about an important part of this mission is getting back our very important scientific data. So as we think about how to transmit that data back up, we either think about an optical tether or even free space repeaters that could send out radio frequency through the ice, such that if the tether might break, you could still have a way of transmitting data. So the Europa STI team, the Signals Through the Ice team, is the team that I've been leading looking at this. And we've actually frozen in tethers into blocks of ice and then sheared them along these dotted lines here. And so the rig will come down and push that central block in one direction with the tether frozen inside, and shears the tether then along the dotted lines. And these tethers have been used previously. These are the types of tethers that have been used with submersibles and polar exploration of the oceans. And so they're pretty hardy tethers, but we really didn't expect them to be as hardy as they turned out to be. Our results really, we did see some damage for these tethers, but it was mostly actually only on the jackets of the tethers. And the tether itself only lost less than 0.1 decibels of signal. So this was like really fantastic, interesting data. There's further tests that we need to do on these tethers, but it's very encouraging for them as a possible mechanism for technology for sending signals back from a cryobot. We also did some modeling in this work to understand what exactly faults might be like on Europa, what kinds of shear forces and strain would it in place if you had the cryobot pass across one of these faults and then have a fault slip occur after passing across there. Another way that we can think about trying to get at these questions before our missions arrive is doing field work. And so we can think about investigating habitability and also how these things work, right? So when we go to the sea ice of Antarctica, this is frozen ice on top of ocean water. We could think of this as a potential analog for a place like Europa. So we take ice cores of the ice and interrogate the ice then for looking for microbes. Are there places where they're in greater abundance in the ice shell? And also, are there other confounding chemistries in this environment that might, challenge our analyses techniques? And then thinking about geysers and plumes at places like Europa potentially, or Enceladus, these mechanisms, this activity, it's really interesting, right? Because we all think about ice and water. Like if you throw your ice cube into your water glass, I mean, what's going to happen? That ice will float, right? The ice is less dense than the water. So what really could drive water up through an ice shell? Well, if you have a drink this evening, I've been drinking a lot of my bubbly waters lately, and I open it up, and what happens? I release the carbon dioxide from my drink, and that bubbly water helps bring material to the surface. I mean, if I shook the can up, that would really bring material to the surface, right? So we've gone out and explored some geysers in Utah, which are cold geysers, and they're just driven by the carbon dioxide that's being released, and it drives the geyser upwards. So we think about these things and we try to understand how these worlds work. And these are some studies we can do here before our missions arrive. So just like to leave you with Onward to Europa, a great, exciting mission. The Clipper mission will really help us assess Europa's habitability. Someday in the future, we'd like to land there, really interrogate the moon for signs of life. And then even further in the future, getting down into that ice shell, getting down into the ocean beneath the ice shell at Europa. Fantastic discoveries really await, I believe, there and other ocean worlds like Europa. So thank you for your time, and I'll happy to entertain questions. Thank you.
Well, thank you so much for this very detailed, as I requested, look at this mission and its many complex parts. And we have time for the Q&A session now, and I think we've queued up quite a few questions. But just to remind everybody, Zoom participants can raise their Zoom hand or type their question in the Zoom Q&A panel. I'll call on Zoom participants who raise their hand in turn to unmute their mics and ask their question. And for those Zoom participants who only want to ask their questions by text and don't want to be heard directly, please just write that in your text and I'll read the question for you. YouTube viewers can text questions in the YouTube chat box and they will be relayed to me. All text questions will be read aloud for everyone to hear. So let's start with a longtime PSW member and Professor Emeritus from the NIH, Carl Merrill. Carl?
Hi, thank you, Larry. You know, since you showed that photograph of the group, and in the photograph is the slab, it begs the question that in one of the series of movies made about 2001, 2010, there was a warning there, and it said, all of these worlds are yours except Europa, attempt no landing there. So I wondered about your comment about that. But also there was another film made later, or I'm not sure, in 2013 called the Europa Report.
Yes.
And in a way that was somewhat prescient because it ended up in disaster if you watched it. In fact, the craft may have fallen over. And that brings up a real question. From what I understand, the gravity effects of Jupiter are such that the surface shifts 10 meters or so each day. So when you survey for a landing site, it seems almost incomprehensible how you can handle that without the whatever it is getting destroyed or falling over, as occurred in that fictional film, Europa. And then one last question. Seth Lloyd at MIT gave a lecture about life deep in the ocean. And he pointed out that there actually is photosynthesis where it's almost pitch dark because, in fact, you have those thermal vents, as you pointed out, and they give off black body radiation. And so you have a Gaussian distribution. So there are some visible photons of light. And he claimed that there's some evidence that there are creatures down there that can capture those few photons. So I wondered if you could comment on that. Thank you. It was a wonderful lecture, and I love the illustrations.
Great. Thanks. Okay, so I'll start with the first one about the monolith. And we actually, not myself, but I believe it was our project scientist, has gotten the blessing from the author of those books and movies that gave Clipper actually the blessing and the allowance to visit Europa. So hopefully we won't run into any issues. Secondly, the tidal forces. Yes, so you're right. So at the places of max bulging, there could be up to about 15 meters of bulging activity. It does somewhat depend on the thickness of the ice shell, but at those locations, and that will be the subjovian and antijovian locations on the surface. So as you move away from those locations, there's less of that bulging motion. And so it's still unlikely that it would cause any too much perturbations unless the ice shell is thin there and you have water. That's the hazard, right, of potentially coming to the surface and causing disruption of the surface that your lander might be sitting on. But yeah, it could be a concern, but it can be considered. And this Europa Clipper will actually get very good measurements of this tidal motion and help to assess where our safe landing sites would be. And then lastly, I actually wasn't aware of the organisms you said that have been able to use the black body radiation. That's really interesting. But in the case for Europa, if that's the case, then those, similar kinds of organisms there could potentially be doing the same thing, I would imagine. And we do see organisms that we are able to measure sort of what they're using for energy. And these are called chemosynthetic organisms that are, at least the majority of their energy comes from the chemistry that they're receiving from these vents. But maybe it's a combination. But thank you.
One of the other aspects, given what you just said, has to do with the fact that in that movie, the Europa report, there are hints of bioluminescence.
Mhm.
And so, of course, that's evolved here on Earth. And so I wondered if anybody has thought about that and building that into your detection, or at least being aware of it, because you may see something like that. And if you're not aware of it, you might miss it. Thank you.
Yes. Yeah, thank you. And that really gets right at trying to learn as much as we can about how life works here and where there might be conditions similar at the Earth to conditions that we expect to be in these ocean worlds, and thinking about how life that we know, I mean, a lot of what we search for is based on what we know. And we do try to think about things that could be different from what we know, but based on what we know, we can do all these field studies and models and things to try to think and predict about what kind of behaviors life might have if it's a similar type of life for what we know.
I have a question from YouTube viewer Scott Matthews. He wants to know, how do you know the magnetic field comes from a salty ocean? Why not from the iron core?
That's a good question, but I think it has to do, and this is not quite my field of expertise, but it has to do, I think, with the amount of fluid so the signal strength has to do with that amount of fluid. And I believe the iron core is potentially believed to be solid iron for Europa. And maybe that's part of the question, right? Is how do we know it's a fluid further out rather than a fluid more concentrated internally? But I think it has to do with the volume of fluid that would be needed to induce the signal that we see. And so the larger ocean could be the potential source for that. But I'm not actually sure. Apologize, that's not my area.
I have a question from Australia. PSW member Frank Robert. Frank?
Hi, Kate. Can you hear me?
Yes.
Yeah.
Good. Absolutely wonderful talk and brilliant graphics. Really conveyed what you were after, which we really appreciate because it's a very complex and fascinating subject. Just quickly, I don't know if you have any possibility to share any data and testing with the ESA DLR triple mission concept, as they are in Antarctic testing of a tunnel bot as well, as my understanding. And it just seemed likely that if you could get around ITAR or the challenges of the US, that you could test design ideas that are not considered protected, I guess. Thanks.
Yeah, thanks, Robert. I'm very interested to talk more with folks on the Triple Project and think about collaborations that might be possible. There are potential, there's previous, collaborations with folks. So it should be something that's possible.
Yeah, I sent your contact info, and I think Christoph will probably be in touch. He was going to be on this call, but it's rather late in where he is, so.
Yeah. Good idea, Larry.
He may not have gotten on.
It's also worth noting, if I'm not interrupting too much, Kate, that one of the people who has been providing quality control feedback to the triple mission asked the question, are you focusing too much on microbes for your assumptions about life? And if something is actively looking back curiously, are you going to see it? So I thought you might enjoy that.
Well, and so kind of along those lines so I work a lot with a biologist at APL. When I came to APL, like my background really isn't in biology, but I also always been fascinated by thinking about astrobiology. And so when I started at APL, I teamed up with him and we've been working on these microfluidic sensors. And the question does come up for us, not quite about whether something's looking back at us, but in the sense of like, we always think that we're going to this place that's going to be, the biomass levels there are going to be extremely low just because it's such a harsh, like extreme environment. But what happens if we get there and we actually are overwhelmed almost with the amount of biology that maybe we get lucky and we find a pocket of biofilm or something that it's almost like will be clogged, right? Is there the potential that we couldn't see the signal because there's too much of it? And so sometimes we do bat around that question and how we would try to address that challenge in our designs.
Also very interested in your test, and then I'll shut up after this, I promise, Larry. The testing of the fracturing of the fiber. I'm sure that you're aware that there's carbon nanotube dope fiber that handles bends much more readily than the normal fiber that is now being used in apartment buildings to turn little corners the way copper can do. And two, that 120 megahertz radio is a lack of absorption region for, as I understand it, for the cryo ice, such that it might be a backup communication method with the tunnel bot, and it's the sub it disgorges could be via that. But of course, then the problem is the water. Once you get the sub out free swimming in the water, how do you get the signal back? Mm-hmm. So, we've been trying to use acoustic, but it's very, very low. Either that or a super low frequency. Like what's used to contact subs on Earth.
Right. Yeah, great. Really all really interesting stuff too that we've been trying to look at some of the free space communication techniques too. And we've mostly been looking at the RF. We had original plans to look at acoustic as well and haven't gotten to that part of it yet. But yeah, because there's also could be fluid in the ice shell as well that could confound some of our signals. So
yeah. Thank you.
It's sort of a vaguely related question about, a penetrating probe, which is what are the energetics of being able to melt through the ice for even an optimistic estimate of how far you have to go? And I noticed that the Clipper doesn't have RTGs, it has solar panels. Mm-hmm. So it's obviously not the lander mission, but how would you see powering a probe to get through the ice?
Yeah, so the most of the probes use the RTGs or some combination of the radiogenic material to power it, and so it really is a melt bot for the most part. Most of the studies, and there's several studies out there that do look at the energetics of heat dissipation in the ice and how much energy you have to input to the tip of the front end of your cryobot to get it to melt. And actually the starting problem is pretty challenging because at the surface where you're in vacuum, anything that you start to melt will immediately vaporize. And so how do you get to the point where you have enough pressure to where you get like a good contact and good heat transfer at the tip to start melting like at a decent rate? And so people are tackling that by either starting with cutting rather than melting and using lasers. Even people have been looking at using lasers to initially get into the ice and get a covering back behind it that they can get this good melting process going. But there's rates that people have been studying and there's some chambers that have been built. I think Bill Stone at Stone Aerospace has built a really tall chamber to test cryobots so that they can be in vacuum and have the ice at the right temperatures and melt things down, probes down through to test them. Yeah, so a lot of research. You're right. Clipper doesn't have any nuclear power. It's solar powered. It was a trade that we looked at earlier in the mission. And most of the time with NASA missions, you really have to prove that you can't do it with solar before.
Yeah, no, I understand.
Yeah. Just as a limited resource. Yeah.
Here's a public perception issue, and plus there's a very limited amount of plutonium at this point. I would take a voice question from Frederica Derema. Frederica?
I just got the unmute screen. Hi, again, like everybody, very exciting, and NASA does this miraculous kind of efforts, and it was really a nice overview of all that. I've been working a little bit myself. I was at the Air Force Office of Scientific Research, the director, but I worked for many years with NASA. So I had a question that was related to the one that was addressed regarding, analogs of life in Earth and oceans, and so you addressed that. So let me ask another question I had. so you talked about cryobots, but also how about coring? And also, I mean, the ice shelves there also can be, in a sense, developed over years. And maybe coring can, in a sense, provide some answer to the question about any potential life, much kind of sooner maybe than the cryobot mission. So
Yeah, so that's a great point. So for the Europa lander mission, that would come first and really interrogate the near subsurface. A coring device could be very informative. It wasn't one of the instruments that was sort of planned by the science definition team. It's just like a study that was done by a group of scientists and engineers. But potentially that could be like a way of bringing sample into the lander and getting at the stratigraphy, right, of your ice versus just a scoop of mixed up ice, so it could be a way of getting at like maybe potentially a meter or so depth of ice to get sample that way first. And so the hope is that the lander mission at the surface would come first and get more information, right, about what exactly is the composition. Like we're going to get the amazing spectrometry data, remote sensing data from Clipper, but then once you go below, just a little bit below the surface, is the material there a little bit, very different. And so a lander will really help us understand that also before we want to send a cryobot to melt all the way.
Right, because it may be something that you can discover very quickly whether there was life there, and that will be really fascinating, exciting. I mean, yeah. Well, again, thanks for the great presentation.
Thank you.
Going to take a couple of questions from YouTube. So we have a question from YouTube viewer Ethan. He asks, with the extreme radiation from Jupiter, what materials in the ice shell and ocean can shield potential life? When would be the next favorable launch window for a follow-up to the surface? In other words, what's the window for sending
for a landed mission?
Yeah.
Okay, great questions. So actually ice is actually a great protector from radiation. So we believe that you only have to, with the landed mission, you'd only have to get, we don't just say we believe, but people have done models and assessments to understand how deep radiation can penetrate into the ice. And it's seen to be about 10 centimeters or so. If you get below that depth, and especially also there's certain regions of Europa's surface that are more irradiated than other regions. So if you stay outside of the highly irradiated regions and you go below 10 centimeters or so of depth, you will get below the region that's most irradiated and be able to really see signs of life there if they exist, so that they haven't been degraded by that radiation at that depth. The second question was when the next favorable launch window. Really, a lander could go anytime. We do want it to go such that we would have information from Clipper transmitted back to the spacecraft. We could launch before having that information and be transmitted that information while we're in transit to Jupiter. And it would be fantastic to send a lander sooner rather than later, because if there is any kind of current activity happening, or we see a plume and we have a plume deposit that's put down on the surface, getting to that deposit as quickly as possible is really key, because the longer it sits on the surface, the more radiation, is occurring on it. So the hope would be that we could send a mission very soon after Clipper, receive Clipper's data that tells us where the most scientifically interesting sites are, as well as safe landing sites for a landed mission.
So I'll sneak a related question in there. So if you're looking for biosignatures and you're looking in, say, in a plume, as opposed to on the surface, what is the effect of the radiation on your ability to detect the biosignatures? So if you're looking for DNA and RNA, you're looking for proteins or amino acids, how degraded will they get before you no longer can actually detect them?
Yeah, that's a great question. There's several things that can happen with collecting samples in a plume as you fly through. In this environment, they could be irradiated if they're floating around out there for some period of time. There are studies that look at how you know, organisms, how hardy they are against radiation. Different organisms last for different lengths of time in those environments. And then also, as you fly through a plume, you know, your spacecraft is moving fairly quickly at a few kilometers per second usually. And the impact, right, of your material in whatever you're using to collect it, it can often actually cause degradation also of your material. And sometimes you can kind of parse out like what it was to start with and how it's been processed, but it's a little bit of you know, people are doing experiments actually to try to understand that with these hypervelocity impact chambers where they shoot material at a plate and they look at what happens to it, and any biosignatures in there. They're actually, so this past week was the Lunar Planetary Science Conference, and there was a presentation on just that, experiments that are being done on this. So if you were planning a mission to fly through a plume to try to look for biosignatures, you really have to, you know, have it going at the right speed, depending on what device you're using for collection. But then you could bring the sample in, and usually all your instruments would be in a radiation, you know, shielded chamber in any case. And that would be the case for Europa landed mission. You'd have to have things protected as you do your sample analyses.
So I'll take a quick one from the web, and then we'll ask a question from Mr. Gansler. The question is, what happened to it? Well, anyway, I'll just ask it. They want to know what the launch vehicle is and whether you're planning to use a Falcon Heavy or it's supposed to go on the SLS, or I think you need a pretty heavy lift vehicle.
Right. So Europa Clipper will go on a commercial launch vehicle. At this time, it has not been decided what the vehicle will be. So there's actually a call out right now for a launch vehicle to be for industry and folks to propose launch vehicles to be used for Clipper.
So it doesn't need a Falcon Heavy class vehicle?
It would be along that, yeah, in that class of vehicles, yeah.
From Mr. Gansler, how long does it take to get data back, i.e. data travel time? And how is the mission ending? Will the spacecraft, and I think several people want to know about this, what's going to happen to Europa Clipper when its mission ends? Are you going to crash it into Jupiter? Like Galileo, what am I thinking? Cassini and
yeah, Cassini went to Saturn. Yeah, Cassini crashed into Saturn. Yeah, it was a great ending. I believe actually the current plan, and we've gone back between Jupiter and Ganymede. I believe our plan is actually to crash onto Ganymede, and because it's known to have such a thick ice shell that there's not concern for any planetary protection concerns. And was there another question in your reading? Sorry, I think I might have.
There was another question, but it's been erased, and my memory is.
Sorry, I think. Answered. Oh, data. The data return.
Answered. Sorry.
Yeah, I remember it was a data return. So I think it's about 90 minutes or so for a straight shot, like for a one-way signal. It's about an hour and a half.
Yeah, I thought while you're on that subject, you could maybe say a few words about the Deep Space Network and traffic on the Deep Space Network and the plans to try to upgrade it and ideas for a much higher bandwidth communications using laser beams, basically.
Oh, well, now you are getting a little bit out of my realm of knowledge. I know that we are thinking of using Arraign, the DSN network, to try to help with communications, and also taking advantage of the European Space Agency's radio antennas. But I'm not actually sure about any potential for the laser transmissions or anything like that.
Yeah, there have been a few, NASA's done a few experiments to try and arrange for something like that, because obviously you can carry a lot more data in a single. I mean,
as a scientist, more data would be fantastic. We will always take the ability to return more data, because that is, a limiting factor especially for these outer planet missions. is being able to data.
Thanks. We have a question from Al Ehrlich. Al, you want to unmute and ask your question?
Am I unmuted?
You are unmuted. We can hear you.
Thank you. You described very well and very interestingly the experiments that are designed to teach us about the surface and maybe below the surface of Europa. I wondered if there was going to be any, at least post-experiment analytics to try to figure out if what you're learning about what's going on the surface teaches you something about the near Jupiter space environment, which is not exactly the focus of the mission, but.
Yes, I mean, so actually some of the instruments actually need to understand some of the Jupiter space environment to kind of remove that signal, if you might say, you know, from the signal they're getting at Europa, to try to understand what is coming from Jupiter compared to what is coming from Europa. And also they are doing comparisons of understanding how Europa affects the maybe more nominal Jupiter environment, right? So the studies will want to look at both environments as much as we can. Our focus is very much on Europa, but we will be doing you know, a bit of science that's related to help us understand what's happening.
Sort of opportunistic observations, which not the focus. Thank you very much.
Yes.
I have a question from David Rabinowitz. David, can you unmute and ask your question? If not, I'll ask it for you. He wants to know what's the bit rate and power for the data downlink, and how stable is Europa's orbit? How long has it been in its current orbit? So take them separately. What's the bit rate and power for the data downlink?
I'm not actually sure what the bit rate is. I could find it in a slide somewhere on my computer, but I'm sorry, I don't know that number off the top of my head.
We can say it's relatively slow compared to like the fiber optic cable that runs at their house.
Yes. A direct link, yeah, a direct hardwire link would be much quicker. So yeah, they'll be slow.
And then he wanted to know about how stable is Europa's orbit, and assuming it's not stable, how long has it been in its current orbit?
Yeah, that's a good question. We do believe that Europa's orbit has changed throughout its history, and we think that that has affected sort of its ice shell evolution. So we think about a cooling and thickening ice shell at Europa, but we do think that there were potential orbits that it was in previously that may have caused periods of warming as well as periods of cooling. So I can't answer directly how long it's been in its current orbit. I don't think we understand that, but we do think it's gone through different orbital parameters and periods of warming and cooling in its history.
Interesting. I have a question from Mike Helton. Mike, can you unmute and ask your question? And if it takes.
Yes, thank you, Larry. Can you hear me okay?
Yes, can hear you.
Okay. Yes, so my question involves flying through the plume, a plume of Europa. And you talked about that as if you were planning to actually do that. Is there actually a mission plan to attempt to target a plume and fly through it, perhaps towards the end of the mission? So if it does any damage to the spacecraft, you won't hurt too much data that you're attempting to collect.
Right. Great question. And you kind of come really to the crux of it in the end of your question, because we do have like this set of goals, right, that we've already done like extreme amounts of planning to make sure we get all the observations that will get at these large questions that we have about Europa. And seeing a plume will be extremely tantalizing. We will want to go towards it as quickly as possible. However, depending on where the plume is, it could require large amounts of our resources, right, to enable us to get to that location, as well as I mentioned, potentially, just causing some risk. So the plan is currently to stick to our original plan, and potentially we may already just happenstance to fly through the plume, as our trajectory is already planned. But if not, it's very likely that any plume material will make its way around Europa and in its environment there, and we could potentially do some sampling of it anyways. But the plan is to make plans to fly through any plumes in a hopefully extended mission. So we will have radiation dosage left. We won't have reached our max radiation dosage, and so we're hopeful that we could act on any discoveries in an extended mission.
Okay, thank you, and a very enlightening presentation. Thank you very much.
Thank you.
Okay, we have a question from Tim Thomas. I think our next to the last question. Tim, you're on. You can, he wants me to read it. Determining habitability is your stated mission objective. What exactly is that when you don't have any idea as what might be inhabiting Europa?
Yeah, that's a great question. Of course, it somewhat depends on life as we know it, but really we understand, life needs a few basic things, right? You need energy to maybe keep this environment habitable. You need something for it to eat. So a source of energy or composition of chemistry that provides something for it to eat. And you need a fluid that enables like the mixing and the interchange of these chemistries that we believe is necessary for life to both, kind of start and evolve. And so, just based on those basic things, we try not to predetermine necessarily like what exactly, say, salinity the ocean has to be at, because potentially there could be an organism that can live in a salinity much higher, say, than an organism here on Earth could. Or we try not to say it has to have so amounts of carbon and nitrogen and that sort of thing. But we see that there is an abundance of chemistries that could support life. So you're right. I mean, it's hard. We're mostly basing how habitable we think Europa is based on life that we know. But we do need to see those things there in, what we would say is a decent amount of abundance or habitable levels for life, but it is based mostly on life that we know.
So I have a related comment. I imagine you've heard or seen Lee Cronin talk about his idea that if you detect a molecule above a certain threshold complexity, that could only be produced by life. So not really asking you to comment on that theory, but you have a mass spec. And
yes.
It's a mass spec that is the one required instrument to do that test.
Right. Well, and this mass spec has extended its mass range over what the Cassini INMS instrument and the mass spec that they had in order to try to see more complex molecules.
So
then
that could be one of your measures.
Mm-hmm.
Interesting. Well, the last question is a nice question to end with. It's a question from YouTube viewer, Beige Price. Kate, you explain complex concepts so clearly. Will you be a mission outreach spokesperson during the Europa Clipper mission?
Yeah, I mean, all of us actually, scientists on the mission are, that's part of, most of us really enjoy, speaking to the public. And of course, it's something that we find very, very exciting. The mission's very exciting. We take all the chances we can get to speak to the public. I speak to my kids' classrooms whenever I get a chance to inspire the next generations, right? Or the fewer down the line generations. I think all of us will be spokespeople, and as I'm on the project side, so maybe I will be maybe a little bit more like, talking about it, but you'll hear about the instruments, you'll get to hear about their fantastic science that they're bringing home, and the pictures that we're going to get are just going to be fantastic, and we just can't wait to get there and be able to tell the public about all the amazing discoveries that we're gonna find.
Well, we all thank you very, very much. You've been a splendid spokesperson.
Thank you.
It's a terrific presentation. You hit all the notes I asked you to.
I tried to give you that detail.
Thank you so much. I wish we could present you with our usual plaque and a signed copy of Volume 1 of the Bulletin, but I'll have to take a rain check on that for when you can come down and join us for dinner and the reception, yes, which you are welcome to do when we're meeting again in person.
Thank you. Thank you so much for having me. And I do look forward to the opportunity to come down sometime. Yeah.
And thank you everybody for joining us.
Thank you, everyone.
Tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on Vimeo and via the PSW Science website. Please share the links with your friends and subscribe to the channel for notifications on new postings. And do not hesitate to join. It's easy to do using the join button on the PSW homepage website homepage, actually. Before you go, we have a few important notes. There's been a change in the schedule. This next speaker was to have been Hod Lipson of Columbia University. Unfortunately, Hod will not be able to give the lecture as scheduled. We have adjusted the schedule accordingly for now. There is some possibility that the date that he was going to lecture will have a different lecturer, but not yet, and it's only 3 weeks away. So for now, we've adjusted the schedule as shown on this slide. But please check the website often for up-to-date information. The next meeting, as presently scheduled, is number 2438. It will be on April 23rd. The speakers will be Simon Bennett and Dan Irwin of the London Crossrail Project. They will be speaking on the construction of the new Elizabeth Line subway, cutting underneath London, sometimes within an arm's length of its highest skyscrapers. The 2439th meeting will be on May 7th. The speaker will be Tony Tyson, distinguished professor of astronomy at University of California, Davis, and chief scientist at the Rubin Observatory, which was formerly known as the LSST. He will be speaking about the potential impacts of satellite constellations like SpaceX's Starlink constellation on astronomical observations and ways to mitigate them. The 2440th meeting will be on May 21st. The speaker will be Bill Powell of the State University of New York College of Environmental Sciences and Forestry. He will be speaking about the chestnut blight and approaches to bringing back a blight-resistant American chestnut tree variety, including conventional and genetic engineering approaches. The 2441st meeting will be on June 4th and will feature the annual Joseph Henry Lecture. The speaker will be Carlo Rovelli, director of the Quantum Gravity Group at the Center for Theoretical Physics in Marseille, France, and he will be speaking on quantum gravity. The 2442nd meeting will be on June 18th, and the speaker will be Steve Stitch, program manager of NASA's Commercial Crew Program. He will be speaking on the Commercial Crew Program and U.S. manned spaceflight. Additional lectures will be posted in turn to the PSW website, www.pswscience.org. Please check there often for updates. And with that, last but not least, please join me in thanking tonight's crew for producing tonight's event, James Heelan, Ann McQueen, and Robin Taylor. Thank you all. And I will now adjourn the 2437th meeting of the Society. I wish everyone a good evening. The meeting is adjourned.